So you may or may not be familiar with this notation for a line equation in 2 or 3 dimensions. Now, if you don't understand where this comes from, then don't worry, this explanation will make it really easy to understand. So let's take a normal line equation that you're familiar with. Let's say y is equal to 3x plus 2. So we know from here that the gradient of this line is 3, and then it has a y-intercept of 2. So what we can do is express the general point on the line in terms of a column vector. So we can say that's equal to x and y. So you're probably familiar with this from GCSE, expressing points in terms of a column vector. Now we can express this only in terms of x. So we can say this is equal to x, because the x is always going to be equal to x, and the y in terms of x is going to be equal to 3x plus 2. So because of that, we can then try and split this vector into 2 separate vectors, one involving x, one involving constant numbers. So I can turn this into x plus 0, 3x plus 2. So now I've got a component of the vector with x involved and a component of the vector with only constant numbers involved. So this is equal to x, 3x plus 0, 2. Now this 0, 2 is basically just a specific point on the line, and that corresponds to this point here, A. Now you'll notice that it has coordinates 0, 2, which is literally just the y-intercept, so we expect that to be the case. Now from this vector, I'm going to factor out an x. So this is equal to x times 1, 3 plus 0, 2. Now this 1, 3 is also quite easily recognizable as the gradient, because for every 1 you go in the x, you go 3 in the y, because the gradient is 3. Now what we can do is rewrite this and equate it to xy, and you'll see how we can actually get this equation here. So we can say that xy is equal, and I'm going to switch these around just to make it the same orientation as that equation there. This is equal to 0, 2 plus x times 1, 3. So we can see that we've got a general point on the line, then we've got a specific point on the line, plus a constant times a direction vector. So this is our gradient vector you can think of, but really it's just telling us the direction that the line is going in. Now rewriting this, we can say that the general point on the line R is equal to a specific point A plus a constant, which now we will call lambda, times the direction vector B. Now this is where the equation comes from, just using the general point xy and making it equal to r, then a specific point calling it a, then our x is our multiplier that we multiply the direction vector by to get to our specific point, and then b is our direction vector. So x and lambda are the same thing, it's just a constant, but we call it lambda just for convention. Now, what lambda actually tells us is how much of the direction vector we need to go along from the specific point, A, to get to the general point R. So for example, if I want to get to a certain point, let's say we have x is equal to 1, then y would be equal to 5. So to get to 1, 5 as our coordinates, I would need to go 1 of the direction vector from this point to get to that point 1, 5. So that's basically what lambda is. It just tells us how much of the direction vector we need to go from the point to get to a specific point on the line. So this is just a quick example that I'll go through to find the vector form of this line equation in 2 dimensions. So first we can see that the gradient is 7. So if each one you go on the x, you go 7 in the y. So we can say that our direction vector b is going to be equal to 1, 7. Our general point is minus 2, but we know that that's the y-intercept. So that means that when x is equal to 0, y is equal to minus 2. So we can say that a is equal to 0, minus 2. Then we can conclude that the vector form of the equation will be r is equal to a, so 0, minus 2, plus lambda times 1, 7. Now let's say that we wanted to find what lambda would be for the x coordinate x is equal to 5. So if x is equal to 5, y would be 7 times 5 minus 2, so y would be equal to 33. So let's make an equation for that. So let's say 533 is equal to 0, minus 2 plus lambda times 1 and 7. So we can use any of the any of the top or bottom lines to basically solve this equation. We'll do the top line since it's the simplest. So we'll take the top line from here. We can say that 5 is equal to 0 plus 1 times lambda, or just lambda. Now that tells us that lambda is equal to 5. And what that means is that we need to go 5 multiples of the direction vector from this point 0 minus 2 to get to our general point 533. So then we can say that for this specific line, we can then say that 533 is equal to 0 minus 2 plus 5 times 1, 7. And hopefully that helps you to understand these vectors a bit better. So we can also use the vector form of a line equation in 3 dimensions. So what I've done here is I've written the components of A as AX and AY, and the components of B as BX and BY. So just to clear out any confusion, it's the same thing as just saying A1, A2, and in 3 dimensions it'll be A3 as well. So these are just different ways of expressing the components of the general point on the line A from this equation here. So rewriting R is equal to A plus lambda B in terms of the split components of each point. So you get R as X and Y, A as AX and AY, so the X and Y components of A, plus lambda times the X component and Y component of B. Now extending this into 3 dimensions, we then get a Z component. So X, Y, Z is equal to AX, AY, AZ, plus lambda times BX, BY, and BZ. Now, what you'll commonly see, especially in the formula booklet, is an equation in Cartesian form in terms of lambda. And I'll show how that's actually formed in a second using this equation here. So what we can do is we can minus this vector here from both sides, and then we can divide both sides by the b, and then that will allow us to solve for lambda simultaneously. So what we can do first is write x minus ax, y minus ay, z minus az as a vector is equal to lambda times bx, by, bz. Then what we can do is multiply this lambda by all 3. So we can, so what I'm going to do that, and then I'm going to write these out as 3 separate equations. So I'm going to do that on this side over here. So we would have x minus ax is equal to lambda, bx. So that's from this first line here, lambda times bx. The second line is going to be y minus ay is equal to lambda by. That's from this line here, lambda times by. Then z minus az is equal to lambda times bz. So that's from this line here, lambda times bz. Now we can see we've got 3 equations for lambda. So what we can then do is rearrange all of these in terms of lambda and making it the subject. So we can say for the first equation, lambda is equal to x minus ax over bx. And then for equation 2, lambda is equal to y minus ay over by. Then we can say for equation 3, lambda is equal to z minus az over bz. Now we can just equate all of these 3 together. So we can say that x minus ax over bx is equal to y minus ay over by, which is equal to z minus az over bz. Now the letters x, y, and z might look a bit different in the formula sheet, but this is basically the general formula and this is where it comes from. So you're just equating the lambdas for the x, y, and z components by rearranging each 3 lines to make lambda the subject and then equating them all together. So you might see it as b1, b2, b3, and a1, a2, a3 as from this equation here. But these are basically just the same thing, so it doesn't matter what the letters say. It just matters that you can use this form and then use it to solve for lambda in certain questions.